We present an end-to-end pipeline for reconstructing a three-dimensional model of a botanical tree, with sufficient geometric and topological accuracy for physical simulation. We record video of a target tree from a pair of cameras mounted on a quadcopter drone. Structure from motion and multi-view stereo techniques produce a point cloud that accurately captures some parts of the tree. We use this point cloud data as a reference to build a simulatable skin mesh. Starting with a generalized cylinder basis, we first create a skin mesh, which is perturbed with the point cloud data to gain additional geometric details. For regions missing point cloud data, we solve a Laplacian to interpolate displacements from resolved areas. We perform mesh smoothing and subdivision, then generate per vertex colors by sampling from the point cloud data. In a controlled environment, general reconstruction techniques can also capture finer twig details. However, it is difficult to recover these finer structures in the wild. Thus, we employ an image annotation approach. We label image space branch and twig positions, as well as topological information. We annotate the branches with thicknesses, and we assign unique identifiers to branching points in order to match features across multiple images. Once one image in a stereo pair has been labeled, we can use epipolar constraints to accelerate the annotation of the second image. The annotator can translate the second image's branch positions along the epipolar lines corresponding to the first image's positions, making for a more streamlined labeling process. Here, we overlay the epipolar lines on top of the second image. We flatten the image annotations into binary segmentation masks, and use these to train a semantic segmentation network. Here, we visualize a semantic segmentation corresponding to frames from the original RGB video. In order to create the segmentation masks, we clustered our training data into two sets, one for dense regions of branches and one for branches more silhouetted against the grass. We train separate networks for each image cluster, and predictions from the two networks are merged back together pixel by pixel based on each pixel's distance to the training cluster means. The videos show one cluster in orange and the other in green. We process the segmentation masks to extract flow fields that estimate branch and twig directions in images. Vectors are visualized in HSV, with hue representing angle and value representing magnitude. We can then use these flow fields to further accelerate the labeling process. We overlay the flow field on top of the image, using blue lines for primary directions and green lines for secondary directions. Given pairs of user-specified start and end points, we use a projection advection scheme to automatically estimate branch thicknesses and trace medial axes through the flow field. Here are the automatically extracted medial axes. Features from the image annotations are triangulated to recover branches and twigs not captured in the original point cloud data. Here, we fade the point cloud in and out. Our model is readily simulatable. The reconstructed triangle meshes are driven by a set of generalized cylinders that are simulated as articulated rigid bodies. The point cloud data can also be driven by the simulation if desired.